It is 4/7/15, and we're going to talk about gas. Talking about gas all week. Woohoo! So, we've been talking about samples of gas. When we have a sample of gas, is it always just one gas? Give me an example of a sample of gas that's more than one gas. You're sitting in it. Yeah. The atmospheric soup we've got, that's, nitrogen, oxygen, carbon dioxide, argon, helium, hydrogen, whatever else. Okay. So we've been talking about volume and pressure and everything else. There are differences between the atoms of different types of gases. Primarily, the difference we've already talked about is what? Their mass. So this is beyond what we do in here, but if two things have different masses, they are capable of exerting different forces on other things. You know this. So those different gases can exert different forces on their container. Let's say we have this balloon and it's got some, well, if you just filled it up yourself, it's probably got some CO2, some nitrogen, some oxygen, and we'll say you got a little bit of argon in your lungs too. Okay. So we've got a combination of gases in this balloon. Each of those is capable of exerting a different pressure on the balloon because they've got different masses. Oxygen is heavier than nitrogen. CO2 is lighter than an oxygen molecule. So we've got all these different gases all exerting different amounts of pressure on the balloon. John Dalton, remember him? What did he do? What did Dalton do? Dalton's what? Dalton's atomic theory, yeah. He did a lot. He did quite a lot in chemistry. Dalton did some work with gas pressures. And what he hypothesized, and I believe later pretty well supported in the lab, was the idea that within that container, whether it's a balloon or a beaker or whatever else it is, we can find the total pressure by just adding up the pressure of every other gas in there. So the total pressure then, if we want to write this algebraically, is the pressure of the CO2 plus the pressure of the N2 plus the pressure of the O2 plus the pressure, I shouldn't have put in another gas, plus the pressure of the argon. So if we know all but one of those, we can solve for the other. Okay, good. And the way this is called Dalton's Law of combined pressures. Total pressure is just the sum of the pressure of all the gases present in a mixture. So the way it's typically written is that messily, P total equals P1 plus P2 plus P3 plus P4 plus, and this can go on forever. You could have 400 gases here. It doesn't matter how many you've got. Okay. Well, great. Why do we care? I'm glad you asked. So this little gadget is called a pneumatic trough, and you saw them on your lab drawer tables, on your list when you checked in at the beginning of the year, and I said, oh yeah, they're near your lab tables. And the things that you will notice about this, I'll do my best Vanna White here, there's a little hole in the bottom, and that little hole connects to a little spigot and to a tube that leads out. And I've got this one knotted off. There's a reason. We put water in that pan, in that collecting pan. And also when you checked in at the very beginning of the year, you had some things like glass squares, ever so creatively named, right? And you had something called a gas collecting bottle. So when we start to talk about reactions that have gases as a product, this is where we start to use things like the gas collecting bottles and the glass squares. Okay? So we can take this glass square and we can put it over the little hole in here. We could block things. I mean, we can also wear it on our head or make jewelry out of it, right? Sure. What are you getting at, Moser? We take this gas collecting bottle, and you'll notice that right now, what have I filled it up with? Just plain water. And it is as full as it can possibly be. I could not fit another drop of water into it. And I can take it, and I can stick that glass square over it. Okay? I suppose I could show that. So I can fill this up, and then I can actually flip it over and I can stick it into the water in this tray. Whoa, nice party trick. What does this have to do with chemistry? Well, I can line up, now once I've got my gas collecting bottle with its mouth underwater, of course I can lift it off the glass square, I can move it all over the place. You know, it's not going to go anyplace. And I did, some of you may be able to see, or I'm going to tell you that I got a little bubble up here. The goal is to not have any bubbles. No bubbles whatsoever. This is just full of water. So actually, let me refill that because I want to do this right. So it's a little tricky, but it can be done. I've done it before. So I get it filled like over the top, and I put that glass, darn it. Get it filled all the way over the top, so it's actually sort of bubbled up a little bit, and then put that glass on. Perfect, no bubbles. Okay, and then I can flip it and get it. Arrgh! Sometimes you can't win. Let me pause this. Fantastic. What are we going to do with this little device here? We're going to collect gas. So when we have a reaction that produces gas as one of the products, how do we measure the volume of the gas that was produced? The primitive way you can do it, and the way that we do it sometimes in some early labs in here, measure all the reactants, then measure all the products that are left. Whatever is missing, whatever your loss of mass is, that must be the gas that escaped. But the slightly more sophisticated way to do it is to actually capture the gas in a vessel like this. So I have here some baking soda and some vinegar, the basis of lots of good home early experiments with chemistry. Okay, and the setup that we have, this is called a gas collection device. We've got a piece of glass tubing running into a stopper, and that glass tube runs to the hole in the bottom of the pneumatic trough. Whoops, retake. And that will allow us to do the following. She's not even in a good mood. Okay, so I will not be able to capture this because it would have to be running in video, and I don't know how to do that, so I'm going to pause this. Okay, so we've now sent some gas from our beaker where the reaction is happening up that tube and up into the gas collecting bottle. So we actually have captured a gas. We could measure the volume of gas that we captured. So you now have a means to actively measure the volume of gas that you have captured, and you can adjust it for temperature. You can adjust for a lot of conditions if you know the pressure and the volume and the temperature. Okay, great. Well, there's just one problem. So what gas is produced, do you know, by the carbon dioxide baking soda reaction? Same one you breathe out, CO2. So that produces CO2. Now, when that CO2 travels up through the water into the gas collection vessel, is that pure CO2? Okay, we're nodding, we're shaking our heads no. Why? Other than the fact that I'm asking and we're talking about mixed gases, and so it must be a mixture. Anybody got anything better than that? Excellent. Had you read that? Oh, you remembered this from reading, or? Okay, good. Yeah! So remember how I said water is only attractive It's only attracted to two other things in the universe, itself and everything else. As those carbon dioxide bubbles travel up through the water, they grab on to water molecules. And some of those water molecules will end up turning into water vapor above the column of water. So we now have a combination of CO2 and water vapor here. So if we want to figure out the pressure of the CO2, we have to somehow use Dalton's Law of partial pressure to subtract out the pressure of the water. How do we find the pressure of the water? Oh dear. Well, I'm going to tell you that you never calculate it, you always look it up. So if you would be so kind as to turn to page 899 in your book, it is, I think, table A something, I don't know what. So we've got this equation that the total pressure of the system is equal to the pressure of the gas plus the pressure of the water. The amount of pressure from the water is going to depend on the temperature of the water. Because, of course, the warmer the water is, the more readily it will vaporize and go up into this gas area. The colder it is, the harder it is to do that. So the temperature of our water bath right now is 20.0 degrees. So what is the partial pressure of water at 20.0 degrees? 17.5, and I believe that is torr.
Yeah,
Millimeters of mercury, torr. Oh, and I should have rearranged first. So P total minus P of water equals the P of our gas, pressure of our gas. And so we've got this as 17.5 torr. How do we get the total pressure? Where does that come from? Well, is that glass collecting bottle exploding or imploding in on itself? So the pressure on the inside of the bottle must be equal to what? Atmospheric pressure. Where do we get atmospheric pressure? From our barometer. And today I would say it is at 766.5. 766.5 is our total pressure. Move that. So we just use a barometer in the lab. So this is 66.5. We have 17.5 torr for our partial water pressure, partial vapor pressure of water. So what's the pressure of the carbon dioxide in there?
749.
749.0, because this is subtraction, so we can go as many decimals as we have. So the partial pressure of our CO2 in there would be 749.0 torr. Okay, I am going to get some homework problems on partial pressures and collecting gases over water. That's what this is called. I will give you, tomorrow you're going to just have time to work on it. Our homework is going to end up being due Friday, not Thursday. And you will have a FIP quiz on Thursday, and we'll kind of answer any questions and review. And then Monday you'll get the pre-lab for the chapter 10/11 bridge lab. Okay? That's it.